We all want our search to be fast, but we also need our search results to be rich, meaningful, and accurate as possible. Thankfully, our next presenters have been doing a lot of work using machine learning tools to make search more accurate and more powerful. I'm so glad they're here today to share some of what they've been working on. Please welcome AWS Senior Applied Scientists James Sharpnack and Xingjian Shi.
Hi, I'm James, and this is Xingjian. We are in AWS AI in the AIR team, and we work on an open source AutoML toolkit called AutoGluon. So that's who we are. We are in California, Santa Clara office. So the smoke here makes us feel right at home. So I'm going to introduce sort of the setup, the scientific setting, and talk about what is semantic multimodal search. And then Xinjian is going to talk about sort of the nuts and bolts of what we're working on and how we can actually achieve it. Okay, so I said semantic multimodal search. So we'll start with the semantic part. So typically what we start with in search is what we call lexical search. So in document retrieval, this means matching either exact strings or keywords to the search query within the documents. So we heard inverted indexing. That's another example of this. So the basic idea is that we just look for these actual queries and stuff. So if, for example, a user was to put in Martha Stewart as a query, then they could get a document that says, actually literally has a string Martha Stewart in it, for example, this first one. Or they might get a string that matches, say, the Stewart keyword. So for example, this second one is about Stewart shops, right? And that wouldn't quite be relevant because unless Martha Stewart happens to own that shop, it's not really relevant to Martha Stewart. And just to sort of foreshadow what we're going to be talking about next, this is basically how BM25 works, which is a standard technology for indexing and retrieval. Okay, so what is semantic search? The basic idea is instead of keyword search, we're going to actually try to match based on the meaning of the documents and the underlying meaning of the queries themselves. So for example, if I was to search for central bank, right, I might find a document that literally matches central bank, right, like the first one here, or I might want to find a document that would match Federal Reserve, that would be about the Federal Reserve, because the Federal Reserve actually is the central bank for the US, right? But of course, central bank, that phrase doesn't actually appear anywhere in that second document. So we want to be able to match based on the underlying meaning. And that's what semantic means. Semantic means meaning. Okay, so that's semantic. We also mentioned multimodality. So what is multimodality? So this is an example of a product page, the Gillette Fusion neck torturer, and and basically this product page has a lot of different information, right? So there's the title, which is a text field. There's this score, which is numeric. There's a price, which is also numeric. There's the image itself, right? And then description, which is also text, and so on, right? And each of these different types of data constitutes a different modality, right? So for example, if we were to say search just based on the images and text, then we would be faced with this problem where we would like to match a text query to documents which now are images plus text. So that's one example of multimodal search. You can also be an example where instead of a text query, your query is actually an image itself. So, facial recognition is a typical example of this for Amazon products. Maybe a user uploads an image for a review, and we want to, say, match it to see if the best matched image actually is the product that they're trying to review. And we could consider doing this with the full product page, right? And so we would be also faced with this exact same problem, but now our query is an image itself. Okay, so that's multimodal search. Both the query and the actual documents can be comprised of different data modalities. So how do we actually accomplish this? So I'm going to sort of go lightly into this, and so hopefully it's clear by the end of this. But we've heard a lot about vector search, right? And that's what we're going to take advantage of. So the basic idea is that we are going to have two different neural nets. We call these two-tower architectures. So one is a neural net dedicated to the query itself, right? So if I have a text, which is, say, a dress with a red bow on it, someone types that into the search, then I would have one neural net that turns that input into a vector. And this vector is dense. So there's a bunch of numbers in the vector, and those numbers tell me something about the underlying meaning of that query, right? And also for the documents, which in the case of just image search, it's just an image. So, and that would have an image embedding neural net associated with it. So this is the second tower in the two-tower architecture. So it takes in an image, spits out another vector, which is our image embedding in this case, or our document embedding. Right? Now, the idea is that we're going to now compare these two, right? So if the red dot in that little scatter plot thing represents the query, where that embedding is, what that vector is, then hopefully we'll find the dress with the red bow on it is actually quite close to it in this embedding space. Maybe nearby is another dress, but not quite the right one, not with the red bow on it. And far away, hopefully, is, say, the picture of the dog. Okay, so that's the basic idea behind this. So there's sort of a classical method that actually uses this. It's one of the earlier examples of this called DSSM, Deep Semantic Similarity Model. And this just matches text queries to text documents, right? And this, you don't have to parse this whole diagram, but the basic idea is that if you have one query and a whole bunch of pre-computed document embeddings, then you can just find the document that's most similar to the query, right? So the query has to be done at inference time in real time, but the document embeddings can be pre-computed and then indexed on. So I told you that we rely on these neural nets, but actually, where do they come from? So the basic idea is that we can use pre-trained embeddings. So say we want to have a neural net that spits out embeddings for text, right? So we're going to rely on what we are calling foundation models. It's sort of the modern name for it. And where do they come from? Well, the basic idea is if we have some data set with some other task, right? So for example, we can take short little documents, maybe clauses, like Barbara is a dog trainer, and then we hide the word dog. So we mask the word dog, and then we try to predict what that masked word is. This is some other artificial task, and it's based on a different data set than probably our data set of interest. But we predict on this, and that allows us to construct this neural net to actually train all of the parameters in it. So this is what's called the BERT model, and it's a really famous foundation model. And we can rely on these. There's tons of these foundation models. A lot of them are named after Sesame Street characters. So.
Okay, yeah. So I will cover the second part of the talk. And really thanks for the introduction from James on the foundation models and the science behind semantic search. So now you have learned that the cutting edge technology in terms of semantic search of how to make search engines more intelligent is we can try to use these pre-trained embedding models. But the first thing, if you are a customer that is already using BM25, the first thing you will ask is how does this pre-trained embedding model perform against BM25? And the team here has conducted this experiments on 4 datasets covering different domains in search. And we measure the performance of a search engine built on top of BM25 and a search engine built on top of extracting vector embeddings and retrieve the related document via k-nearest neighbor. And here are the results. Here we evaluate a quantity called NDCG at 10. There is no need to worry about the detailed meaning of this quantity. All you need to know is that this is a quantity that can give you a signal about the performance of the search engine and how your customers may be engaging, how they may like this search engine. And it's a higher and better, this quantity. And what we notice is that actually the pre-trained embedding model does not always outperform BM25. So now if you are a customer that is already using BM25, maybe you will start to hesitate of whether should I actually adopt the pre-trained embedding model or not. So next, I will introduce 2 techniques that can improve over this naive pipeline that can actually very consistently outperform BM25 by integrating with the pre-trained embedding models. The first technique is that we can hybridize BM25 and the vector embedding models. So here is an example. Assume that you have a query and you have a bunch of documents, and we are designing the search as a multi-stage pipeline. In the first pipeline, we use BM25 to retrieve the top 100 related documents to the query. And in the second stage, based on the results we obtain from the first stage, we further calculate hybrid scores that hybridize the score measured by BM25 and the score measured by the pre-trained embedding model, so we get our final top 10 retrieval. And this solution, compared to our naive pipeline of directly running KNN over these pre-trained embedding models, this solution has lower latency because BM25 is very well optimized, and adding BM25 as an intermediate stage actually improves the latency. The interesting thing is we can see that this solution is starting to consistently outperform BM25. So here are the results on the 4 data sets that we measured. These 4 data sets from different domains like biomedical, medical, finance, and general question answering. We can see so these columns are the performance of the BM25, our naive pipeline of applying vector embedding models, and the hybrid BM25. Although hybrid BM25 does not always perform the best, but if we compare the performance of hybrid BM25 and BM25, we can see that it wins in 100% cases. In fact, internally, we have also conducted experiments on datasets from more domains, and we are seeing the winning rate of this hybrid solution over BM25 to be close to 100. So you can see now we have one solution that is consistently outperform BM25, and you like to use this solution because your search engine is essentially more intelligent because you have the pre-trained models being able to capture the semantic meaning of the queries and documents. So can we further improve the system? And the answer is yes. We can further improve the system if you have relevance data that is tied to the task. So if you have relevance data, for relevance data, I'm meaning that it's the real behavioral data from the users that are interacting with the search engine, if you have this relevance data, you can fine-tune the pre-trained embedding models via this dataset. And we further compare the performance of this model that has been fine-tuned, which is the last column of this table. And we see that on all the data sets, we are fine-tuning the model achieve the best performance. So fine-tuning really helps here. Now we know that there are two techniques that we can adopt. Both techniques can give you consistent improvement over BM25. The next question is, how can we use such techniques? So although it sounds like straightforward, but it now involves the idea of machine learning. And most machine learning algorithms are quite painful and involve lots of advanced technologies. And usually if for a company, if the company starts to think about putting machine learning into production, it will really need to go these three stages. The first stage, it needs to bring the data sets in. It needs to prepare the data sets for training the model. And after maybe some data scientists have created the data sets, we need very giant effort in training these models and evaluating these models, and later on to deploy these models for the real prediction. The problem that machine learning can be very crazy and costs really a lot are actually these two stages. The model training and model inference require tons of engineering and science cost. So what we are offering here is we are automating the process of training the models and making predictions with a new toolkit called AutoGluon. AutoGluon is an open source AutoML toolkit. It can give you state-of-the-art multimodal AutoML performance. And for multimodal AutoML, we are seeing that AutoGluon is able to automatically build models on dataset that contain image, text, tabular data, and even time series. And this is open source, and you can check our website at auto.gluon.ai. For using AutoGluon to build models, the first step is to prepare the multimodal data into this multimodal DataFrame format. And here is an example from it's from a pet adoption speed dataset. So the goal is to predict the adoption speed of the pets. And the speed of adoption is related to multiple features. It's related to the image of the pet. It is related to the text description of the pet from other people. It's also related to how many photos have been taken for this pet. And we are able to just prepare it into the multimodal data frame format. We have image column, which essentially store the URLs or local paths of these images. We have the description column, which stores the descriptions in the raw text. If you have experience in data science and have used pandas, you can immediately notice that the multimodal data frame is an extension of pandas data frame. We are supporting more types of data via this format. And after you have prepared the data into the multimodal data frame format, training models is super simple. It only involves 3 lines of codes. And by just writing 3 lines of codes, you are able to get access to all the state-of-the-art foundation models. You are able to access state-of-the-art foundation models provided by Hugging Face, InTim, and also Clip. For these 3 lines, it's very straightforward. You first create the predictor. After you have created the predictor, you call predictor.fit to train the model. And after you have trained the model, you call predictor.predict to get the prediction on the data sets. One thing is, as I have just shown, foundation model is not a panacea here. There are still cases that traditional machine learning models perform well. So to cover these corner cases so that our AutoML solution can perform well in the whole spectrum, we also support a functionality called auto ensemble. Via the auto ensemble functionality, we essentially can bring in the best of both worlds by combining the powerful foundation models and these standard machine learning models like GBM and XGBoost. And all you need to do is to write the same 3 lines of codes. So we have see that these 3 lines of codes are really powerful. It can be users are able to use it to build very powerful models that lead to very strong results, lead to top ranks in competitions that real data scientists are participating in. Here are a list of our ranks in competitions at Kaggle and Machine Hack. And we can see that by just using 3 lines of codes, the AutoGluon is able to outperform most of the data scientists in these competitions. So in the upcoming AutoGluon 0.6, we are going to release a new feature that can help users to extract semantic embeddings that can be useful for building the search engine. Since AutoGluon is open source, this feature has actually it's already there in our master version, so you can already try it out by installing the pre-release of AutoGluon. And here I have attached a code snip example of how to use this feature in AutoGluon. It's pretty simple. You will only need to create the predictor and specifying the pipeline to be feature extraction. And for the foundation model, we support all kinds of foundation models that are available in Hugging Face. So you can pick any kind of model you like to use in the sentence transformer package. And after you have created the predictor, you can extract embeddings for the documents and also for the query. Once you have extracted these embeddings, you are free to do anything you like to do. For example, building KNN index for the document embeddings, and also maybe integrate with other search backends. And our roadmap is actually to bring together the state-of-the-art AutoML toolkit and the state-of-the-art search engine backend, OpenSearch. We try to integrate AutoGluon with OpenSearch, and in the future, OpenSearch will be able to, users of OpenSearch will be able to extract pre-trained embeddings to improve their search engine. And also in the future, via the AutoML functionality in AutoGluon, users will be able to automatically fine-tune these embedding models via the user's relevance data. So that's all for the presentation, and thank you.